lucky. Feel so lucky, feel so 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 lucky. You gotta notice, hey, I'm falling in love. You're feeling something, yeah. You cannot control. Just in time you came, and you changed all my perspective. Yes, in time you came, and I love it, I love it. It's so great to have you in my life, make me feel so lucky, yeah. It's so great to have you in my life, make me feel so lucky, yeah. Feel so lucky, yeah. Feel so lucky, yeah. Feel so lucky, feel so lucky, yeah. Feel so lucky, feel so lucky. Feel so lucky, feel so lucky. Feel so lucky, feel so lucky.
A pair of jeans, a shirt or two. We didn't pack as if we weren't going back. It doesn't matter if it's true. I've got a feeling love will give us what we lack. The world is waiting up. The world is waiting half a step beyond our door. Yeah. And if it's not enough, I wanna see the stuff the world has got in store. I wanna take it all in, I'm falling. The cityscape by night, wanna catch in my photos. Where you go, every corner twice as bright. They'll be my treasures forever. When I can't hold you tight, I'll see the Stockholm lights. The Stockholm lights, the Stockholm lights. Tomorrow feels a year away, like the seconds, the beginning and the end. But if in time it's yesterday, your picture's gonna bring it home to me again. The world is waiting up. The world is waiting half a step beyond our door. And if it's not enough, I wanna see the stuff the world has got in store. I wanna take it all in, I'm falling. The cityscape by night, wanna catch in my photos. Where you go, every corner twice as bright. They'll be my treasures forever. When I can't hold you tight, I'll see the Stockholm lights. The Stockholm lights, the Stockholm lights.
It's YouTube Music. Download the app today and get a trial of Music Premium on us. Restrictions apply.
You and me, we easy when we collide. No one walks away easy. I never thought you'd be the one. I never meant to take your heart. I never felt so hard. I never meant to be the one. I never thought I'd break your heart. And after the stars have crumbled to dust, we still feel the warmth.
say goodbye or ever leave this stuff behind. When it's good, it's amazing. When it's bad, it's uneasy. I wouldn't have it another way. There's no other way. Yeah. When it hurts like this, ever like, wait it, ever like, ever like, ever like, What does perfect even mean? Is there even such a thing? Oh, can we switch up all the rules and imagine a utopia? Darling, I'm just so fed up with these expectations. They keep weighing me down. My heart is begging me to get the hell out of my head. I'm trying to live inside the upside down for a minute and pretend. Honey, I'm a perfect 10. Whoa, whoa. Honey, I'm a perfect 10. Whoa, whoa. And if I say it enough, it gets ingrained in my head, and I start to see. Honey, I'm a perfect 10. 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 Whoa. Honey, I'm a perfect 10. Honey, I'm a perfect 10. Disgusted with myself, and I'm disgusted with the way we're told to have a certain face. I stood and wait because we aren't pixels on a screen. No, we're human, we breathe. Every single thing we see curated, it's overrated. These expectations, they keep weighing me down. My heart is begging me to get the hell out of my head. I'm trying to live inside the upside down for a minute and pretend. Honey, I'm a perfect 10. Whoa. Honey, I'm a perfect 10. Whoa. And if I say it enough, it gets ingrained in my head, and I start to think.
People haven't joined.
Honey, I'm a perfect 10. Honey, I'm a perfect 10. Honey, I'm a perfect 10. Whoa. Honey, I'm a perfect 10. 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 Oh.
On my own, but I don't know why you hit the road, but you don't
Presentation visible,
realize
guys.
I won't look back when you're around.
Yes, Farhan, it's visible
I
for
won't
me.
think twice when you are gone. Don't hesitate to call me back, 'cause I won't be there. I won't look back when you're around. I won't think twice when you are gone. Don't hesitate to call me back, 'cause I won't be there. I won't look back. 'Cause I won't look back.
Yes, this is
I
working.
won't look back.
Yeah.
Okay, I think we can get started then. Yep, we can start now. Ganesh?
Hello guys. Hello.
Hello.
Yeah.
All right, let's get started then.
All right. So
Yeah. Guys, here we are for our first webinar of the QPower Quantum series. QPower is a quantum computing community recently formed under the Microsoft Student Partners Initiative. So our focus as a community would be to empower knowledge to one and every person in our community and outside our community about quantum computing, about Azure Quantum, Microsoft Q Sharp as a programming language for quantum computing, then quantum machine learning, quantum cryptography, and its applications in medicine. So if you're an AI enthusiast, or if you're into medicine, or if you're into law school, or you're into computer security, wherever you are, we have something for you. So don't forget to stay with us till the end of the webinar series. We have really exciting stuff coming up. We also have a hackathon at the end of our series. All right, so let's get started with the first event. So I'm Syed Farhan Ahmed. I'm the founder of this QPower community. This was started, as I already said, under the MSP program, Microsoft Student Partners, a few months back. And I am myself a Microsoft Student Partner from India. I'm also an engineering student from Bangalore, RV College of Engineering. I'm doing my BTech in Electronics and Communications Engineering. All right. So let's get started with today's topic, Intro to Quantum Computing. So in my talk, I'm going to talk about, I'm going to introduce you to classical computing. I'll start with how the third industrial revolution began and how, current classical computers look like. Then I'm going to talk about dual nature of matter, the wave nature and particle nature of matter. You might think, why is this important? Well, if you want to transition into quantum computing, it's really important to understand how matter behaves as both waves and particles. That's one of the building blocks of quantum computers. Then I'm going to talk a little bit about quantum computing, about qubits, and a few applications, so that you can get some interest into this particular subject. All right, let's get started, guys. Let's talk about the industrial revolutions. The first industrial revolution began in 1765. So we had steam engines which were invented during that time. Everyone is aware of that. We have studied that in history, in our school curriculum. Then we had second industrial revolution, which saw the emergence of new energy sources. We had electricity, we had gas and oil based vehicles and things coming up, which was in 1870s. And finally, in 1969, from 1969, the third industrial revolution began. This is where we saw the emergence of computers, basically classical computers. We saw electronics, we saw telecommunications emerging. So what was so special about this industrial revolution? So in 1940s, we had a transistor which was invented. This was the biggest invention man could have ever made. A transistor made out of silicon, which can act as a switch, and it has certain properties. So if you're into electronics, you would have studied the properties, but let's not delve into too deep details about a transistor. So a transistor can act as a switch. So you know about a switch, you turn it on, the light turns on, you turn it off, the light turns off. It's that simple as that. But a transistor can also act as a switch under certain conditions. So if you have certain voltage conditions given or certain current conditions given to a transistor, on the right side, you can see it's as simple as it allows the current to flow or it doesn't allow the current to flow. That's as simple. That was invented in 1940s. And because of that, we had classical computers coming up from 1969s. So let's try and understand what classical computers are. So a classical computer has a CPU or a motherboard, you can say, which is made up of silicon, which has lots and lots of transistors. The motherboards, or basically the processors these days that we have billions of transistors on them. I'm not talking about thousands or millions, but billions of transistors. And together, these billions of transistors, sort of help us do everyday tasks that we do in our computer systems. All right, so remember that transistors can go on and off, right? And hence comes the concept of bits. So bits are nothing but either we have two different states, either it's 0 or 1. 0 is nothing but the off state and 1 is nothing but the on state. And we have different sets of programming languages that have been developed, and we use them in classical computers these days. Basic examples are C, C++, Python, and various other voice controlled languages which are of higher generations. You would have studied about generations of computers. So what is so special about these bits? So millions and billions of bits together perform these kind of huge tasks that computers or classical supercomputers these days are doing for weather forecasting, for machine learning, for different purposes. So how does all this begin? We have a basic adder. You add two numbers, you add two binary numbers together. You have, for example, you take a decimal number, 10 and 11, you add them together, you convert that to binary, they are added in a computer system, and you get the output in binary, which is again being converted to decimal. So 10 plus 11 is nothing but 21. So from adders, multipliers are made. So multipliers are actually made from adders, and using these multipliers, millions of multipliers together, we can do the complex operations that can be performed today on these computers. All right. So yeah, so what were classical bits again? They were nothing but zeros and ones. And we have different logic gates like the AND gate, we have the OR gate, and different types of gates which performs different logic. And based on these logics, we get adders, multipliers, subtractors, etc. Madhav, the next speaker, will be talking in detail about this. All right. So classical computers, you all know that. Just have to remember that it's based on two states, either 0 or 1. Let me talk about Moore's law. So people must be aware about what Moore's law is, right? It states that the number of transistors doubles about every 2 years. Let's not worry about the costs. Let's worry about the transistors. So if on a chip, the number of transistors are doubling every year, the area remaining the same, there will come a time wherein the size of the transistors will become so small, which is happening today. We have billions of transistors in a very small processor which is of millimeter square size area. So you can see the size of one of the transistors today. Okay, it's not actually 14 nanometers. We have 7 nanometer process. We have transistors of much smaller size these days. And you can see the red blood cell or the HIV virus, which is much bigger than the current transistors that we have. So you can see that we are reaching the end of Moore's law. We can no more double the number of transistors on the chip. We can no more, include more and more units of processing power on our chip. So what are we actually looking at? We are looking at alternate ways of computing. We are looking at parallel processors. We are looking at different processors, working in union as a single chip, or we are looking into a different computing paradigm. That is quantum computing. Let's now talk about that. So what is a quantum computer? Let me brief you about that. So there will be, two quantum states which define the basic unit of information processing, and we call them qubits. We'll talk about qubits in a bit. Let's talk about, the algorithms which this particular quantum computer uses. In classical computers, we have zeros and ones, and these are nothing but regulated by transistors. These transistors work together in units, in millions, or in thousands and millions together to perform complex operations. But the way they perform it is sequential. But in quantum computers, we have parallelism included. So what happens once you have parallelism? You have exponential amount of processing power. Let's talk about that later. Okay, so you can see that a normal computer, a classical computer on the right side, let's assume the red color threads that you see are processes that a computer has to complete. So there are multiple processes and the computer is completing them one by one. That's a classical computer. But in a quantum computer, they can be done simultaneously. That's the power of parallelism in a quantum computer. To understand much better, let me give you an example. Do you identify this maze? Okay, this is not from Harry Potter and the Goblet of Fire. This is actually from the Maze Runner. So if Thomas and Minho knew the power of quantum computing, then they would have figured out the outlets of the maze within seconds, rather than they spent actually 3 years mapping the maze. They were mapping the maze sequentially. There was one runner, there were two runners, there were three runners. They were running in different directions, and they were trying to map the maze. So that is nothing what classical computers do these days. If you have a maze, they're going to find out the endpoint of the maze. If there are, say, 1,000 endpoints, they will run through every single endpoint sequentially. But for quantum computers, to give you an example, they will run all the 1,000 cases at once. If provided the proper number of qubits, they do stuff exponentially. Okay. So let's talk about qubits. So bits are nothing but zeros and ones. So what are these qubits? They are also zeros and ones. What is the hype about them? What is so special about them? So the speciality is that a qubit can be in a superposition. Okay, superposition is nothing but it can be in a state of 0 and 1 at the same time. The laws of quantum physics works in a similar way. So quantum computers are built based on laws of quantum physics, and the beauty of quantum computing is you don't have to know a lot about the laws of quantum physics. You don't have to be a PhD in quantum physics to learn quantum computing or work with quantum computers. That's the beauty of quantum computing. So you can see that qubit can take any of the state. The blue color thing which you see right in that sphere, the qubit can take any state between 0 and 1, but a bit can only take one state, which is either 0 or 1. That's the beauty of qubit. So they are inherently probabilistic. They have a certain probability of being 0 and the certain probability of being 1. So you know how probabilities work, right? If the probability of it being 0 is 0.2, then the probability of it being 1 is 0.8. So it's 1 minus the probability of the other. That's how these qubits work. Let's now talk about dual nature of matter. A few of us must have studied this in high school about dual nature of matter, that wave particle duality, as matter can behave as both waves and particles. But let me just brush through it. You must not remember, or maybe some of you must have not studied. No issues, we can just go through it once again. All right. So the famous the famous experiment that was taking place was known as the double slit experiment. So what happens in a double slit experiment is, so for now I'm talking about particle nature of matter. So you have a gun which is shooting out bullets. All right. Let me just take the laser pointer. Oh, all right. Let be a pen. So you have a gun which is shooting out bullets in a uniform manner in this direction, and you have two different slits or two different passages very small that can allow the bullets to pass through them. Okay, so either the bullet can pass through this slit or it can pass through this slit. And then you have a movable detector. It will detect where where the bullet will strike this particular backstop. We have a backstop, and wherever the bullet strikes, we then create a probability distribution. So if you're using this particular slit, this will be your probability distribution, P1. And if you're using the slit 2, P2 will be your probability distribution. And if you add them together, we're talking about particles right now, just keep that in mind. This would be your final probability distribution. So basically what it means is, if you're shooting out bullets from a gun, you have two different slits, then the probability of the bullets landing on the on the backstop will be in this fashion, in this probability fashion. Let's now talk about waves. So simple example, you have a wave generator. You take you can create waves in water using your two hands yourselves. Let's talk about the wave nature now. So you're giving out a wave. Again, you have two different slits. You're passing the wave, and then the wave will strike the wall or the backstop once again. All right, so you can see that the probability distribution is not similar to the way which we had earlier in the bullets or in the particle nature. Here we have interference happening between these two waves. So a wave is passing through. We have two different slits, and we have two different waves coming out from these two slits. From here, we have two different waves coming out. They are interfering amongst each other, and we have different interference patterns. You can see that we have crests and troughs. In the waves, we have crests and troughs, and finally the interference pattern looks something like this. Increasing intensity, and the intensity is reducing as you move. So wherever you can see the wave, the output, that is nothing but constructive interference, and where there is darkness, that is destructive interference. This is how waves work, and the earlier case was how particles work. Let's now talk about dual nature of matter. Let's shoot out electrons instead of guns. So what would we actually expect? Electrons are nothing but particles, right? So what we would actually expect is, okay, let it shoot out. This kind of probability distribution, right? This kind of probability distribution, but we can see different kinds of interference patterns. So this is nothing but your maxima. There is destructive interference. Then again, there is constructive interference happening. So what can we infer from this experiment? We can infer that electrons can behave both as waves and particles. So it's taking the interference pattern of a wave and it's striking the wall as a bullet. So that's the dual nature of matter, okay? And we have different probability distributions. That's what gives rise to the property of a qubit, as to, you know, being either zero, not either 0 or 1, a superposition of both 0 and 1 together. All right. Let's talk about a few applications of quantum computers. Before that, let me talk about molecular dynamics. So what happens in molecular dynamic simulations? So computer simulations are a method for analyzing physical movements of atoms and molecules. So we allow and interact. We allow the molecules and atoms to interact with each other, and the feedback can be visualized. Okay. So once we visualize the feedback, we can understand the molecules and atoms better. I would request all the others to mute their mics, please. Thank you. And a simple case I will talk about is the human ACHE enzyme. So ACHE stands for acetylcholinesterase. So what does this enzyme do? It's a human neuron. It terminates the signal transconductance. So what's the transconductance that we are talking about? You can see a neuron impulse on the left side, right? So what's actually happening? Two neurons are trying to communicate between each other using electrochemical impulses. And what this particular enzyme is doing on the right side, okay? This enzyme, terminates the signal transconductance. So, for example, if you touch something hot, you know that it is something hot, and you draw back your hand instantly. If this enzyme is not present, ACHE enzyme, you will keep drawing your hand back again and again, even if you're not touching something hot. Okay, so that's the power of this enzyme. And using the power of this enzyme, if we have people suffering from neuron disorders or psychological disorders, it can be used for treating those diseases. And these kind of enzyme interactions are very, very important in understanding how the enzyme works. We have to create a drug for or a medicine for this particular neuron disorder. So we need to understand how the enzyme works, and so we have different simulations.
Farhan, I guess your mic went off.
Hello.
Yeah, it's fine now.
Yeah. What about the human ACHE enzyme? Did you guys hear that?
Yes, we heard that.
Completely. All right. Fine then. So to summarize, basically, we need to understand how this enzyme interacts with its neighbors, and And to understand the interactions, we need a quantum computer. A lot of parallelism is required, and a classical computer is very slow in this regard. All right. So similarly, drug discovery for COVID-19 can be done in a similar way. So this is a VR simulation by Nano. It's a company Nano. You can Google it later on. So what it does is it allows you to view the simulations in a VR environment, virtual reality environment. And if you have a quantum processor in the background, it can speed up your operations millions of times better than what a classical computer would do. Let's talk about machine learning, SVM. So what is a support vector machine? So support vector machines are nothing but supervised learning models for classification problems. As you can see on the 2D plane below, we have red and blue dots. You have to classify them as red and as blue. You have to draw a circle basically on that 2D plane. So drawing a circle on that 2D plane, processing that is very, very complicated. Therefore, you would apply a kernel trick. You would convert that 2D space into a three-dimensional space. So you're taking that 2D space, you're folding it into a three-dimensional space, and then your kernel separator, the classifier which you will apply, will be a plane. Instead of a circle, it's going to be a plane, which will be much simpler for your computer to process. Now, if you're using a classical computer for converting this 2D space into 3D space, the amount of processing power required is a lot. You need a lot of parallel processing. There again, a quantum computer steps in. It can help you really well in quantum machine learning algorithms. Let's talk about cryptography. Everyone has seen the screen, right? You have WhatsApp chats. You can see end-to-end encryption. If you're chatting with someone new, or even if you're chatting with anyone, there will be an end-to-end encryption on the top. So what if I tell you in the next 5 years or in the next 10 years, your chats can be unlocked by anyone who has access to the database of WhatsApp. Even if your messages are encrypted, if we have quantum computers, these messages can be decrypted very easily, using the power of quantum. So quantum cryptography has various diverse applications. I'm not the right person to talk about quantum cryptography, but yeah, I have given you a basic overview of how it looks like. All right, that's it for my presentation. Thank you guys. You can follow me on Twitter or on LinkedIn. It's on screen. Thanks a lot. If you have any questions, you can leave that in the chat and I'll try to answer them.
Yeah. Hi, is my screen visible?
Yeah. Okay, someone has asked, will the video be available tomorrow? Yes, it will be on YouTube. You can access it with the same link.
Can you guys hear me?
Yeah. Go
Okay,
ahead.
so hi, my name is Madhav, and I'll be giving somewhat of a theoretical point of view of quantum information and quantum gates. So quantum computing as a subject can get really overwhelming, especially if you're a beginner. And like I'm still a beginner, and it still gets highly overwhelming for me at points of time. So I'll try to make it as fun and light as possible. So yeah, let's get started. And I'm in no way an expert. So if you guys find some mistake in what I'm saying, please do correct me. I'd appreciate it. So first things first, we need to ask ourselves is what is computing in general? Computing is somewhat of a loosely used term. It's loosely thrown around. But actually, what does it mean to compute something? And does it come at a cost? Is it a physical process? And can we quantify the outcome of what it means to compute something? So what it means to compute something is basically taking some amount of data which is raw and converting it to some amount of data which is meaningful, or in a generic definition, converting data to information. But that too, that again is a high level definition if we really want to understand where the roots of quantum computing start. So this is some extremely scary looking formula if at first when you look at it. So Claude Shannon, who was an American computer scientist and mathematician, so he gave this formula to basically quantify information. And if you sort of look closely at it, you'll realize that it's a formula which was also given by Boltzmann to give the entropy of an isolated system, which is basically the second law of thermodynamics. So why is there a correlation? Not why. Can we draw a correlation between that concept and information? Can we draw a correlation between entropy and information? Is the fundamental question that you should ask. And the answer is obviously yes, we can. But how do we draw that correlation? How do we correlate entropy and information? So, firstly, entropy is loosely defined. Entropy is a measure of randomness, it's a measure of disorderliness. And high entropy means highly chaotic, and less entropy means more organized or less chaotic. So, if you look at this formula, it basically sums up probability over all states and takes the log of that. And let's look at it from a purely computer point of view. So if you have, suppose, n states, so the probability of you picking any one of those states would be 1 by n. So each p of I would be 1 by n. And if you take b to be equal to 2, then the formula would simplify to log n base 2. So which would lead to, if you put n equal to 2, you would get 1. So that basically means that 2 bits of one state can represent 2 bits of information. 2 bits of information can represent one state, 0 or 1, heads or tails, something like that, and then so on and so forth. So if you have 2 bits, you can represent 4 bits of information, 0, 0, 0, 1, 1, 0, 1, 1, and so on and so forth. Now, the reason that I thought that this should be included and this should be brought up is because it's highly important to help us understand the difference between quantum gates and classical gates. So, as I said, high entropy is unorganized and low entropy is organized. And if you go from a state of higher entropy to a state of lower entropy, it basically means you're doing some work, right? So if you suppose have an extremely dirty room, which I know I have because of the lockdown, and if I've been nagged to clean it, I'll obviously do some amount of work to organize things here and there, some amount of mental frustration that, oh, why do I have to do this, and things like that. So I am spending some amount of my own energy to move from a state of higher entropy to a state of lower entropy. Now, this might seem a little bit out of place, but just bear with me. It'll all fall into place soon enough. So yeah, why quantum and why bits? Like why are those two words even together? So the thing is, all topics in quantum computing from the very start till some of the advanced topics, all of them sort of elegantly merge into one another, and it's highly fascinating and satisfying to sort of realize how they do that. So the idea initially was, what if we can use some of the quantum mechanical systems for processing information? So how would we even do that? How would we go about computing something? And by computing something, if I had to put it formally, it would be the system and the process should have a finite amount of distinct states that it can be in, and so on and so forth. So classical bits or just bits have two distinct states, 0 or 1, but entropy, as I said. So if you sort of go ahead and ask a question such as, why only 2 states? Why does one bit have only 2 states of information, 0 or 1? Why not more than 2? So that answer again comes from entropy. And the second law of thermodynamics states that the entropy of an isolated system would remain constant over time, would never decrease over time, rather. So if you have 0 or 1, you can't have more states or less number of states for a single entity of information. It has to be 0 or 1 only to sort of maintain that law. Quantum bits, on the other hand, can be anything in between 0 or 1. So it can be a superposition of 0 or 1, which is, yeah, I gave away, I should have said spoiler alert, but yeah. So if it's something in between 0 and 1, we call that to be a superposition. And that's a property of quantum mechanics. So formally, a qubit is a quantum system by itself, which represents the smallest unit of quantum information. And so this is what it would look like. So if you could represent your bits, the state 0 or the off state as a vector as 1, 0, and 1 as a vector 0, 1. And if you look closely, you'll see that these two are perpendicular to each other. So you have 0 like this and 1 like this. And then you have a general representation of a qubit, which is somewhere in between 0 and 1. It can be 0 or 1 or something in between as well. And yeah, here you have 0, 1, and then a qubit can be 0 and 1 at the same time. So alpha and beta, basically here, the intuition would be to say that it has alpha amount of state 0 in it and beta amount of state 1 in it. And can any vector be a qubit by itself? Answer obviously would be no. So given a vector, you need some way to classify it to be a qubit. So given a vector, you should be able to say that if this is a qubit or not. And the way you would do that is by intuitively looking at this. So if you have the state 0, which is this, so the 0 vector here, the length of the 0 vector is 1, and the length of the 1 vector is 1 again. And the qubit, the state psi, is some part 0, some part 1. So it's some part of 0, some part of 1. So it cannot be more than 1, because if it's more than 1, it would represent more amount of information than you started with initially. And that's not possible. It cannot be less than 1, because if it's less than 1, then you have loss of information, which you obviously don't want it to happen. So it has to be exactly 1. The length of this vector has to be exactly 1. So that's the condition for some vector to be a qubit. And all of this is in a complex vector space. So all of this is you can't model a qubit in a real vector space. So this is the condition. So you have mod alpha square plus mod beta square equals 1, which ironically, if you consider mod alpha square to be the probability that the qubit is in state 0, and mod beta squared to be the probability that it is in state 1, it's sort of surreal to see that sum of probabilities is equal to 1, and it just fits. So you have mod alpha square plus mod beta square equals 1. If you had a multi-qubit state, so that means if a quantum system had more than one qubit, then still this condition would hold for all of the coefficient of each of the states. Yeah, so vectors and vector spaces. Generic definition, vector has both magnitude and direction. A vector space over a field F is a set of objects where two conditions hold. So operation of two vectors is closed, meaning that if you add two vectors, it has to be in the same set of vectors. The resultant has to be has to belong to the same set of vectors. And the operation of multiplying a vector with a scalar also is closed. So we represent qubits as state vectors, so they're known as state vectors. This is a state vector. 0 is a state vector. 1 is a state vector. 0 and 1 are known as standard bases, and psi would be the state vector. Yeah. So block sphere. Yeah. So this is something that's highly useful, and honestly, it's one of the most fascinating things there is in quantum computing, and the way qubits are represented. So this is something extremely ingenious thought by someone. So what they did was they decided to represent a qubit in a Hilbert space. So Hilbert is a complex vector space. So they decided to represent a qubit in the form of a sphere of unit radius. So any point on the sphere represents a qubit. And the reason that, and this is another representation for the qubit. So alpha, e power I, phi, beta. So phi is the relative angle between 0 and 1. So there would be other stuff, other parameters like theta and things like that, which would come from the spherical coordinate system. But those won't really matter in the representation of qubits, because when you go to measure a qubit, those values become inconsequential by the laws of quantum mechanics. And the reason I said that this is something that's really fascinating is, in the previous slides, we saw that 1 and 0 are perpendicular to each other. But if in a Bloch sphere, they appear at opposite ends of, so this is known as North Pole and South Pole, and they appear at opposite ends of each other. So the reason that happens is because this is 0 and 1 aren't Hilbert orthogonal. They are physically orthogonal. And what that means is that for something to be Hilbert orthogonal, if it's in one state, it cannot be in the other state. So Z and X also aren't Hilbert orthogonal as such, because if you measure a qubit which is in a superposition somewhere over here, then it would have some amount in Z and X. But Z and X are physically orthogonal. There is actually a really fascinating and nice article about this. I'll maybe share it with the organizers and they can put it up. Maybe that might be more helpful than me trying to explain it. Yeah. Wow, explaining it itself overwhelmed me a little bit. I'm sorry if I'm going a little fast, or are there any questions? No, cool. So as I said before, qubits are nothing but vectors in a 2 power n Hilbert space. And a very important operation is the inner product. Inner product is equivalent to the dot product basically, but you can't call it a dot product of two vectors. So the inner product is basically, you have two notations, which is the ket and the bra. So ket is basically the normal notation, which is alpha and beta, and bra is the complex conjugate of the ket, which is alpha star beta star. And you multiply these two vectors and you get alpha alpha star beta beta star, which is mod alpha square plus mod beta square, which is equal to 1. So more formally put, to check whether a vector is a qubit or not, is you take the inner product of the vector with itself, and if that gives you 1, then it is a qubit. If not, it's not a qubit. Yeah, so this is something that's highly, I fanboy over this topic the most in quantum computing, because there are a lot of really cool theoretical ways to look at measuring a system in quantum. So one of them is Schrodinger's cat, and one of the ways to interpret the result of Schrodinger's cat is via the multiverse interpretation of quantum mechanics. I highly suggest, if you guys are interested, look it up and watch a few YouTube videos or something on it. It's really cool. So how do you actually measure something, and how does this fit down our trip to physics? So the way we measure a qubit in some state is you take the inner product of the qubit with that state, and the answer you get, you take the absolute value of that and square it. So if you want to measure the qubit in state 0, you would take the inner product of psi with 0 and square it, and you would get mod alpha square. Similarly for state 1, which is mod beta square. And as I said earlier, these two represent the probabilities of the qubit being in states 0 and 1 respectively, or in general in some state which you measure it in. Yeah, so matrices and their importance in quantum computing. So in linear algebra, you can think of a matrix that transforms a given vector to some other vector, or to another vector space entirely. So think of a matrix as an operation that transforms a vector. So columns of matrices, consider columns of matrices as vectors, and these columns are the transform standard basis when this operation is applied. So that's just a fancy way of saying that the columns of the matrices would be what the 0 vector and the 1 vector would be after you apply that gate to the qubit. And these operations are termed as gates. Gates. Oh yeah, sorry about that. I guess we all were a little bored during the lockdown. Yeah, so these gates are so first important property of a quantum gate is that they are unitary matrices, which means that u dagger u equals u dagger equals I. So dagger is nothing but the conjugate transpose of a matrix. So dagger is the quantum mechanical notation of a conjugate transpose. So they are unitary matrices, which means that they are reversible, which is another very important property of quantum gates. And yeah, so before we go on to this, so I'm sure most of you know what the classical gates such as AND OR do, what they do. So they take in, okay, so let's stick to the standard AND and OR gate. So they take in two inputs and they go to a single output. So if you look at it in terms of entropy, as we talked about earlier, you are taking a system with two entities to a system with one entity. So if you take two entities, you could have four states in that 0, 0, 0, 1, 1, 0, and 1, 1. But you are taking them to a system with one entity, which means you can have two states in that. So you are taking them to 0 or 1. So that again can be interpreted as you moving from a level of higher entropy to a level of lower entropy. And that again goes to say that you are doing some amount of work in doing that, in moving from a state of higher entropy to a state of lower entropy. And that means there is some loss of energy that's taking place while you're doing these computations of AND or XOR. All of those gates have a loss of energy, except maybe the classical NOT gate, which is one state to one state. So in terms of entropy, at least there's no energy loss, but then there might be other factors due to which there might be loss of energy. So that again is fundamental. That again is a important difference between these gates. So in quantum gates, the entropy remains constant, and classical gates aren't reversible. So if I give you a black box, you don't know what gate is inside. And if I give you just the output, the result, and there is some circuit inside the black box, and I ask you to guess what circuit it is, you can't really reverse the result to get back the original inputs which you had in, which resulted in that output. You can maybe guess the circuit by sort of, applying a few trial and error gates, but then you won't really be able to guess the exact input that was provided. So that's another important difference, which is that classical gates are irreversible, but quantum gates are, reversible. And that being said, let's move on to the actual core of quantum gates. So the first set of quantum gates is the Pauli gates. So the Pauli gates are highly famous and well known in quantum computing. So you have three types of Pauli gates, X, Y, and Z. So the Pauli X gate is equivalent to the classical NOT gate. So it basically flips the standard basis. So from 0 it goes to 1, and from 1 it goes to 0, as you can see in this visualization. So from 0 it will go to 1. And if you are in 1 and you apply it, it will go back to 0. And it rotates the qubit above the x-axis. So that's why it's called Pauli X. X of 0 is 1 and X of 1 is 0. Pauli Z gate again, similar to Pauli X, it rotates the vector about the z-axis. So it would take z of 0 to, it won't change the qubit when it's in state 0. but it will add a negative phase to the qubit when it's in state 1. Or in other words, it adds a phase of pi radians to the qubit. So it adds a relative phase of pi. So that's why, as you can see here, it goes from 1 to the opposite side. So you get -1. And also another interesting thing about Z, the poly Z, is that Z of the plus state. So plus state is what you get. Okay, I'll come back to this after another slide. So poly Y gate is similar to X and Z. So it rotates the qubit about the Y axis. And you can use poly Y gate to, when you apply poly Y to the standard basis, that is 0 and 1, you get a set of circularly polarized states, which is circularly left polarized and circularly right polarized. Now, in the beginning, I said that it's really satisfying to see how different theoretical concepts sort of gel into one another to sort of, give a correlation between the different things that there are available. So this is just a theoretical model of gates, but if you were to sort of actually build hardware to implement gates, what you would do is you could implement some of these gates with the help of polarizers, beam splitters, and wave plates and things like that. And the way that you model polarizers, beam splitters, and wave plates is with something known as Jones matrices. And Jones matrices, after a bunch of calculation and reducing it down, you sort of realize that Jones matrices reduce to some of the standard quantum gates that are available. So if you want the Z, the part of the wave, the part of the light wave along the x-axis to remain, you would model a poly X gate. And if you want along the Y, you would model a poly Y gate, and so on and so forth. And applying some of these gates together can sort of give you highly powerful tools to sort of process information. So you can entangle states, which will be talked about later on. And you can entangle states with the help of multiple gates. And what's really cool to see is gates are nothing but simple matrices. And matrices sort of, you can visualize them as taking a vector at one point in the block sphere to just another point in the block sphere. And you can manipulate the vector as much as you want and in whatever direction you want and by how much ever angle you want. And it's all up to you. You're the boss in whatever you want to do with the qubit. So the Y gate sort of looks like this. So Y of 0 is equivalent to Ix. X and Z are poly X, poly Z. So poly X, poly Z, 0. So Z of 0 is nothing but 0. So Ix 0, which is I. And Y of 1 is Ix Z1 minus I, and so on and so forth. And the Hadamard gate, so this is one of the most popular gates in quantum computing, the Hadamard gate. So the Hadamard gate is where all the fancy stuff starts when you're building quantum programs and simulating quantum circuits. So Hadamard gate, if you don't really know, okay, so if you have some qubit which is in state 0, but you want a qubit which is somewhere here, then you're like, oh, okay, so some superposition has to be involved. Let me apply a Hadamard gate. So Hadamard gate is probably one of the most popular gates. So what it does is it puts a qubit into a superposition. So if you have a qubit in state 0, you would go to state plus. So plus is nothing but an equal superposition between 0 and 1. So I'm sorry, I forgot to add the mathematical form of plus. So plus is nothing but 1 by root 2 into 0 plus 1. So that basically states that 0 and 1 have equal probabilities of being measured. So if you measure it along 0, you would have 1 by root 2 whole square probability. If you measure it along 1, you would have 1 by root 2 whole square probability, which is 1. And h of 1 is minus. So minus is basically 1 by root 2, 0 minus 1. So there's a phase difference again there, which is added. Phase difference of pi, which is added. And that again has a probability of 1 by root 2 being measured. And I think as far as I know, at least from whatever I've learned, Hadamard gate is sort of highly useful in quantum cryptography and quantum key distribution schemes because of the fact that it puts a qubit into a superposition. And when you measure a qubit into a superposition, you can't really say whether the bit that was encoded was sent was 0 or 1 with surety. So if you receive some qubit which is in state plus, and if you measure it, you have a 50% chance that it was initially in state 0 and 50% chance that it was initially in state 1. And so that's the reason that you can't fully know for a fact what the original information was that was sent. And that's sort of something that's important in quantum key distribution schemes. And also you can sort of detect that if there are intruders or if there are people eavesdropping on your communication. So because as soon as someone tries to observe something, that will break down the superposition and you get to know about it. And the moment you get to know that the superposition has collapsed, you can sort of terminate communication then and there and restart over. And that's highly secure. It's sort of 100%, theoretically it's 100% secure. Obviously there are some, you can get your way around it by some clever tricks here and there. So yeah, what do they look like? They look like matrices. So I, which is the identity matrix. So this matrix is sort of usually overlooked in quantum computing, but I by itself is a gate known as the identity gate. And the reason that it's important to know, it's important to look at I as a gate by itself is because in quantum simulators, when you don't have a gate applied to one of the qubits, it means that there's an I gate applied there. And if you want to sort of dig deeper onto how the calculations are performed, what it would do is it would combine, suppose there is X and there is qubit 1, qubit 2, and there is a poly X gate here, but there's nothing on qubit 2. So what it would do is it would combine X and I, then it would combine the states of first and second qubit and then apply the computation on it and then do a decomposition and then get back the original states. That's how it's performed. So that's why I've put it here. So you have the X, Y, and Z. So as I told earlier, look at the columns of the matrices as transformed state standard basis vectors. So if this is 0 and 1, this is 0, this is 1. So 0 on X would become 1, so you have 0, 1, and 1 on X would become 0, so you have 1 and 0. Similarly for all of these. So as I said before, so H on 0 would become 1 by root 2, 0 and 1, and 1 by root 2, 0 and minus 1. Yeah, so as I said, yeah, coming back to this, so Z sort of acts as a flip for the Hadamard basis. So plus and minus is known as the Hadamard basis. So Z on plus gives minus and Z on minus gives plus. And quantum gates are reversible. So H of 0 gives plus and H of plus gives 0. H of 1 gives minus and H of minus gives back 1. So this is applicable to any quantum gate, not just Hadamard. So another easy gate is the R5 gate, which is basically a rotation by phi radians around the z-axis. So if phi is pi by 4, it would model a gate known as the T gate, which adds a phase of pi by 4. Then if phi is pi by 2, it adds a phase of pi by 2. And if you want to subtract a phase of pi by 4, you do T dagger, which you just take the conjugate transpose of this and you get this. Take the conjugate transpose of this and you see this is basically subtracting a phase of pi by 2. So how many gates have we covered so far? I think we covered all of them. Okay, I don't think so. See, that's the thing, right? So literally there are infinite points on the block sphere that can be represented with qubits. And you can have infinite number of transformations that can take place from one point to the next. So instead of remembering all of them, there's sort of a general 2-qubit gate which you can model, which is given by this formula. So you have theta, phi, and lambda as the parameters for this gate. So phi is sort of the rotation angle, theta is the vertical angle, and so on and so forth. And you can model Hadamard, Poly X, Y, Z, all of that using just this one formula. Yeah, so the overview of single qubit operations would be, so the X gate would transform 1 to 0 and 0 to 1. Hadamard would transform 1 to -1. So this 180 here represents relative phase. So -1 has a relative phase of 180 degrees or pi radians. And 0 on H would give 0, the plus state, which has 0 degrees of relative phase. And so on and so forth. So if you have here S, you add some amount of phase, you get back this, and Z, you get back this, and so on and so forth. So multiple qubits, if I want to perform operations on, so this is known as the control NOT gate. So this performs the operation of, so this is known as the target, this is known as the control bit. So if the target is 1, it would flip the control bit. So it would basically perform an X operation, a poly X operation on the Y, on this second, on the target qubit. So this is the gate, this is the matrix for the C0 gate. So this basically states that if you have 0, 0, which means the control is 0, target is 0, so it would be unchanged. If you have 0, 1, it would still be unchanged, but if you have 1, 0, it would flip to 1, 1 because target control is 1, target would be flipped from 0 to 1. So 1, 1 is this, and 1, 1 would be flipped to 1, 0, which is this. So that's how you can derive basically any form of control gate. So you can have control Z, control Y, control H, control U3 in general. So this is the general form of a control gate. So this is, you can put in a poly matrix here to get the poly control gate. You can put in the Hadamard matrix here, and so on and so forth. Completely up to you. So a bigger gate would be a double control gate. So only if both A1 and A2 are 1, B would be flipped from 0 to 1. So this is basically A1 and A2 XOR B. So only if both are 1, would B be flipped back, would B be flipped. So similar logic as a control gate. So you have this, and then so on and so forth. And here again is your poly gate, the poly X gate. You can put poly Y, poly Z, so on, and whatever you deem necessary. So that's the Toffoli gate. It's known as the Toffoli gate. Yeah, so coming to sort of a game to understand the power of quantum gates. So this is sort of really cool if you think about it. So heads or tails. So the rules are something like this. The coin starts off with heads facing up. The first move is made by your opponent. The second move is made by you. But the trick is that during these moves, neither you nor your opponent can see the coin. And the third move is again made by your opponent. And in the end, if there's tails which is facing up, you win, or else your opponent would win. And the thing is that we are going to consider two scenarios. That is, if your opponent has a classical computer, and if your opponent is of classical nature, and if your opponent has quantum abilities. Are the two things that we are going to consider now. So classically, if you don't know what the coin is, if you're not looking at it, and if you decide to flip it or not flip it, there is a 50% chance of you winning or your opponent winning. So you can either decide to flip the coin or leave it as it is, but you can't see it. So the final details of this would be, you model heads as the state 0, you model tails as the state 1.
Sorry to interrupt, Madhav. We have shared the link in the YouTube chat for the coin flip challenge.
All right. Okay, thanks. So this is a web app that I had made for another talk, and I'll be presenting the data which I collected from that. But at the end of the session, I'll also present the data which you guys send in. So you go ahead and sort of play around with it and click how many ever times you want, and we'll see classical versus quantum how it turns out to be. So a flip can be modeled as a poly X gate, and a no flip can be modeled as an identity gate. So 0 to 1 would be heads to tails. So you flip it, and it can land on either heads or tails. So classically, you would have a 50% chance of winning or losing. But because of some amounts of bias and things like that, this was the data that was collected. So the audience sort of won in this round, but as you can see, not by a very good margin. But when your opponent has a quantum computer, things tend to be very different. And no matter how hard you try, no matter how many times you try, the enemy is so formidable that you have literally zero chance of winning. So your opponent will always win if he or she has quantum abilities. It's the identity gate here, identity matrix, X being poly X, H being Hadamard. So H of 0 is plus, H of plus is 0, X of plus is plus. It doesn't change. X has no effect on the Hadamard basis whatsoever. And H of plus again is 0 because quantum gates are reversible. So in the classical case, if you sort of model it as a circuit, it would look something like this. So your opponent flips the coin, you flip the coin, and you flip the coin, your opponent flips the coin, and you decide to leave it as it is. Your opponent decides to leave it as it is. So X, and ID, and then you measure it, and whatever the result is would be known after that. So this is what the circuit for that would look like. But in the quantum case, it would be that no matter what you choose here, if your opponent has a Hadamard gate, he or she can put the qubit into a superposition of either plus or minus, and in the first move itself, your opponent can put the qubit into a superposition of plus, and then in the end, your opponent can apply the Hadamard gate back and get back 0 with 100% certainty. So your opponent would always win in that case. You would always lose. So yeah, that's my time, I guess. That's my talk. Thanks. And if you have anything at all that you would like to correct, or if you have any questions later on, you can always reach me at my email. Yeah, thanks.
Okay, all right.
Thanks for joining us, Madhav.
So very great presentation so far. Let me share my presentation here. Okay, 1 second. So are you guys seeing my screen? Fine?
Yeah, it's fine. Go ahead.
All right, so we've had 2 great presentations so far. And what I'm going to do, or I'm going to try to do, and I've prepared to do so. I hope in the end of this presentation, you guys don't leave here saying, oh, wow, I wish he had prepared better. But I'll try to talk about what some of the companies are doing regarding quantum computing. And as it has been said before, we don't need to be experts in quantum physics to do quantum computing. As a matter of fact, we don't need to understand anything about quantum mechanics. We just need to understand the math behind it, because the math works. And that's the principle that drove all quantum mechanics research for decades, because for a long time people didn't know whether uh, quantum mechanics or the opposite theories were the ones that would prevail. Anyway, so Microsoft's doing a lot of quantum, and so the first question is, what exactly are they doing? And also, can I do that? Because if you pause for a second and if you look back for think about the first or the second or even the 10th time you've heard about quantum, you may have been confused or scared or even terrified about the possibility of working with it. But it's quite possible. And there are a lot of companies that are working towards researching technology and things that enable quantum computing to be a more accessible reality. But to deliver on that promise of quantum computing and to solve all the problems that will forever change our futures, we need a quantum computer that scales, which is something that we don't have right now. So a lot of companies are focused on groundbreaking innovations at every layer of quantum stack, since applications and solutions to cryogenic control or understanding how to control qubits. And Microsoft has a unique approach that's been pushing the boundaries of computing to create uh, unprecedented possibilities for the world. And they have a lot of companies they're working with. We can say, for example, Ford is working with quantum one qubit, and a lot of other companies that are working within many fields: chemistry, pharmaceuticals, cryptography, and any other thing that's been mentioned here before in the slide. If you think about it, there is a possibility of application. Microsoft, for example, one of the things that they have been offering is Azure Quantum, which is basically a full stack open cloud ecosystem to bring the benefits of quantum computing to people and organizations all over the world. And there are many sets of quantum solutions available there, and we can check its tools, Azure Quantum Tools, and there are even learning tutorials about the quantum development kit, such as the quantum katas that we will experiment a little bit with them. And we can develop, for example, there's Q Sharp that's going to be mentioned afterwards, and there are many possible applications that can be done today. Microsoft has a quantum scholar group that anyone can apply to join to try to contribute and benefit of the information. There are internship programs for PhD students and now for undergraduate students. So there is something quite accessible, and I dare to say that it's very accessible actually, more than people think. So if you ever consider about like migrating to from I don't know, uh, front end development to quantum, you'll be more than welcome to do so. And this is one of the goals that we have here, is to provide tools for you to learn by yourself if your college doesn't offer a quantum program, and experiment and to be in touch with quantum researchers all over the world. It's quite possible today. And we all probably have heard about many advantages that a quantum computer has over a classical computer. But to understand that, we need to look back in time. So, remember when I said that neither quantum mechanics or any other like possible theory could be prevalent? So this is what happened. This guy named Niels Bohr, he decided to propose a theory to explain a certain behavior that began to be observed with lamps, actually, going back further in time. So the lamp, the light bulb lamp, triggered the biggest technological revolution in physics that's still ongoing. So anyway, I'm not going to dive deep into the physics or anything because we need to take a break a little bit. We've had two great presentations that delved into math a lot, and I want to refresh our brains before we prepare for another round of theory with Q Sharp, and then the Kahoot session, which is going to be awesome. But basically, Bohr wanted to understand the light particles, the small particles, and he proposed a theory that was completely absurd to Einstein. So absurd that he coined some very famous expressions such as God doesn't play dice with the world, or so the moon is still there even when I'm not looking to it. But anyway, this debate took years to be solved. Who was right, quantum mechanics or the other theory that was proposed by Einstein, Rosen, and another guy here in the US? Anyway, there's this physician, this hippie physician called John Bell, that he decided to solve that problem. And it's funny because his inspirations were kind of not orthodox. You can dig in a little deep and you will find some very funny stories about extrasensorial perception or telepathy. But anyway, no matter what drove him to do his research, he used some very interesting and quite simple probability, actually, to prove Einstein wrong. And this guy, he ran an experiment that pretty much confirmed that quantum mechanics works. And from that, I mean, people were already doing a lot of, I'm sorry. Okay. Is it back?
No, not
Can you
yet.
guys?
Not yet.
Okay. All right. Yeah, I think it's back now.
Yeah, go ahead.
Okay.
Yes.
All right. So back to the hippie guy. The hippie guy just confirmed something that physics all over the world were already working on because, I mean, it worked. No matter how absurd quantum physics, quantum mechanics, or any quantum theory looks like, and we've all heard during these presentations things such as this is 0 and 1 at the same time. Oh, this is, I don't know, it's nuts. But the math behind it works. Stick to the math. So, anyway, uh, because of all this story and his experiment and blah, 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 we know today that quantum computing was made possible. And it has, in fact, many advantages over a classical computer. One of such advantages, it's the superior speed searching databases. And if any of you here is familiar with algorithms and data structures or things like that, we know how important it is to dive in deep into more efficient algorithms for searching elements in a certain database and big O notation and all those things. And a guy named Grover, working on a previous problem that came, I'm not going to go into that problem. Madhav talked a little bit about that problem, which is the Deutsch problem. It's a classical problem in computing, but that quantum actually solves it faster than classical. But this is a practical application, and it's called the Grover algorithms. And imagine that box I drew down there, and it has n elements with n different colors. But I want to find the pink guy, okay? So in classical computing, I will take an average. uh, of X time, I'm trying to avoid the math. And in worst case, I'm going to go through all of the boxes to find, right? But quantum computing, we can find it in roughly square root of n steps using the amplitude amplification trick. And behind, hiding in the image, is the algorithm implemented in Q sharp in order to execute that. So a quadratic speedup in the search, which is what happened with Grover algorithm, it's quite a substantial time saver for finding marked items in long lists. And in addition to that, this algorithm doesn't use the list internal structure, which makes it generic. So this is why it provides a quadratic quantum speedup for many, many classical problems. And from that, we have the we have other algorithms and other solutions that were solved. It's of course it's important to note that not always quantum offers better solutions than classical because of its non-deterministic characteristic. And of course, we have some a sum in classical and a sum in quantum. It wouldn't make a difference, but we need to understand that if we pair up classical and quantum, we can have many, many, many possibilities. And I don't know, thinking about that. So where do we go from here? We've been hearing about these solutions. We've been hearing about many possibilities and many things. And we still don't understand a lot of things in quantum. For example, why is there superposition? No one is able to answer that like precisely. Or what is the mechanism of wave collapse between two particles separated by space and time, which allows their entanglement, for example, which is something that astonishes me, really. Is it really something that works faster than light speed or not? Anyway, I am quite sure that the physician or the researcher that is alive nowadays to answer these questions might be among us. Who knows? It could be Farhan. It could be Madhav. It could be Ganesh. Who knows? Our friend Ganesh here. Hey, Ganesh. Anyway, I just want to wrap up with a quote. I'm sure most of us have heard the quote, shut up and calculate, but not everyone knows the right context in which it was given. And this whole interview is an amazing one. So if you can look up that article and read about it, I'm going to read this. So if I were forced to sum up in one sentence what the Copenhagen interpretation, which is the one given by Bohr, says to me, it would be shut up and calculate. But I won't shut up. I would rather celebrate the strangeness of quantum theory than deny it, because I believe it still has interesting things to teach us about how certain powerful but flawed verbal and mental tools we once took for granted continue to infect our thinking in subtly hidden ways. I don't think anybody, even Bohr, has done an adequate job of extracting these lessons. This was said in 1989. I'm pretty sure the same thing can be said today. What I mean with this is if you want to study quantum, go for it. That's what we're trying to do here. We're trying to show it's possible. You don't need to understand everything right now. You probably won't. Trust the math, go with it, go along with it, study, research. Who knows? Maybe in the future you can be the person who's going to solve, I don't know, one of the hardest questions that we may have in physics. Thank you very much. I hope I did a good time, and I'm going to give some spare time for you guys to work on the other things. And if you want to get in touch with me to hear about the advanced math or physics involved, I can talk about it as well. And make sure to find our group. The link is there. And anyway, thank you very much for you guys for your attention.
Yeah, Ricardo, that was motivational. So we have a question from the audience. Tanvesh asked, you mentioned that Microsoft Scholars group. So how can we join that?
I will post the link on the YouTube chat in a moment.
Oh, that sounds awesome. Thanks.
Okay, before we begin with QDK and Q Sharp programming, let me tell you we have a Kahoot session after the programming sessions, and the top 3 winners will get a special certificate. All right.
Wow, special certificate sounds amazing.
Yeah.
And especially thanks, Ricardo. You really encouraged me to go delve deeper into quantum programming. I'm seriously more excited now. So, Microsoft Quantum Development Kit. Well, there is a lot of quantum, but definitely Microsoft is at your aid. It helps you a lot. So, what is QDK? QDK comprises of a wide range of tools, and being a developer, it gives you everything that you need to start writing your quantum programs. Beginning with Q-Sharp libraries, we have been using many languages. Libraries and API are nothing new to us. Now let's talk about various target machines. We have resource estimators, simulators, and a lot of state quantum simulators. Now, what's special about full state quantum simulators is that you can easily use them, just fun around, just run, debug, and like you can do everything. You can start your quantum programming journey there. But there's just a little problem that it just works with a few qubits. So you cannot be a very, very professional programmer over there, but it's a great way to start. And also, Microsoft provides a lot of tools to you. We have a Visual Studio Code, a VS Code, and there are real good extensions. And Python and Jupyter notebooks also provide packages for that. We'll soon try to make some short clips for that so that you can get started with the VS Code or Visual Studio. So don't worry about that. Also, there is a plus for C Sharp and Python developers that there is a proper API documentation for pairing Q Sharp with the classical host languages. So that's a lot, and trust me, this is going to really help you a lot. It has helped me a lot because I was afraid of quantum computing because I feel it's a research field. But now I know Microsoft has helped, IBM is helping too. That now we can get started too. So now that yeah, I love Q Sharp, and we'll be doing a little hands-on. But before that, we need to understand Q Sharp, and for that, I will invite Rohit to give introduction to Q Sharp.
All right. Thanks, Pallavi. Let me share my screen. Okay, so guys, here is a repository for you. It's github.com/qpowered/msps/workshops. You can go here. We have created a nice service where you can do all the stuff related to quantum using Microsoft's very own Q Sharp language. So go to this URL and then click on workshop 1 introduction to quantum computing and click on this icon, this launch binder icon, and it will open up a repository, a Jupyter lab basically, wherein you can start your coding. So a natural model for quantum computing is to treat the quantum computer as a coprocessor. So like we have GPUs, FPGAs, etc., wherein it basically helps a host computer to perform certain kind of operations because they are focused on doing some kind of work very well. So Quantum or Q sharp is a domain specific language used for expressing quantum algorithms. It is used for writing subroutines that execute on an adjunct quantum processors. So let's have a look at the type model of Q sharp. So Q sharp is a strongly typed language such that careful use of these types can help the compiler to provide strong guarantees about Q sharp programs at compile time. So it has a lot of primitive types to offer, such as integers, big integers, double, and we have special qubit type, which represent a quantum bit, and then we have polytypes, which Madhav already talked about. There are 4 polygates, so polytype represent each of those gates. And then we have a special data type for result for storing the result of the measurements. We can declare immutable variables by using the let keyword. So like this, as you can see, by default the variables are immutable, but if we want to create mutable variables, then we can use the mutable keyword, and we can change its value by using the set statements. Q sharp also has array types. So arrays are data structures which can store a fixed size of collection of elements of same data types. So we can use the square rotation here to create array types, and this is a special syntax. It is also known as a range. It basically tells us from where to start, how much steps are we allowed to take with each iteration, and where to end. So this syntax basically tells us to form an array which consists of 2 and 4 as elements. So by default, arrays are of course immutable in Q sharp. So if we were to change elements of an array, we cannot simply do like we do in some other languages such as C++ or Java. We cannot just use subscripts here. We have special update and reassign statements or copy and update expressions. We are going to talk about them in a little while. Alternatively, we can declare an array by using the new keyword, as you can see here. Let 0 equal to new integer bracket 13, which basically declare an integer array, signed int array, which consists of 13 integer. Another type is tuple, which Q sharp has to offer. It is similar to array, but it holds different kind of data items into it. So just like this, we can have a tuple consisting of an integer and a bool. Then we have operation and function types. So quantum operation or Q sharp operations are quantum subroutines. That is that they are those subroutine which are going to be executed on a quantum processor. So we have functions which are subroutines that are callable through an host machine, and they are going to be running on a host processor. Together they are known as callables. Then we have a special facility here to create user defined types. We can use new type statements to create new data types as our likings. So here I have created a complex data type, which actually has two doubles or double precision floating point number. They can be named, as you can see, I have used RE to represent the real part of it, and I am to represent the imaginary part. And now we can use this newly created type just like the other types. We can pass it to a function, we can create different instances of it, and etc. So here is an example. We can just this is the syntax of Q sharp. This is how we declare what kind of parameters this function accepts. So A is a type of complex data type, and B is also complex, and we can the member by using the resolution operator, which is this double colon, and we can just return it. Let's have a look at statements and other constructs. So just like any other language, we have comments which begin with 2 forward slashes. There is no facility of multi-line comments, so that's sad, but we have documentation comments which begin with triple slashes. Then we have namespaces. So namespace is a declarative region that provides scope to identifiers inside of it so as to, you know, prevent name clashes. So we can open a namespace by using open keyword. So everything that is defined under the microsoft.quantum.intrinsic will be accessible under the ns namespace. Let's have a look at the control flow. So just like any other language, Q Sharp also has a facility for iteration. We can use for loop for that. So for loop supports iteration over an integer range or an array. So this is a simple syntax for qubit and qubits. We can perform this operation on that qubit. Qubit is a of type array of qubit. Again, here is the range syntax. So IDX will run from 0 to whatever the length this qubits has minus 1. Both are inclusive in ranges. And this is the statement update and reassign statement that I was talking about. So if we want to change an element present at index, we have to use this special syntax w slash equal to and then whatever the value we want to assign to it. We have these special repeat until success loops. These are special to the Q sharp language. So these basically follow the repeat until success pattern which we have in the quantum computing field. So the block is repeated until a condition is met. Just like here, Hadamard gate is used to create a equal superposition of the 0 computational state and the 1 computational state. So until we have result as 0, we want this computation to repeat itself. This is basically the idea of repeat until success loop. Then we have while loops. Now a special thing to note here is that Q sharp does support while loops, but it does not support them in operations. It supports while loop only within functions. So we have a really familiar syntax here. Until these two conditions are unmet, we are going to repeat these operations. Let's talk about some conditional statement here. So Q sharp supports if conditions for conditional execution. Also, we can nest those conditions if we want to. A really simple syntax here. If result is 1, this 1 is a special keyword special to Q sharp. It basically means computational 1 which exists in quantum computing. Okay, then about qubit management. So basically whenever we allocate a qubit, we get it in the 0 computational state. So whenever we deallocate them, they are expected to be in 0 state again, unless the quantum machine, right now we are using simulators, but whenever we are going to run that code on real quantum machines, this is how they expect the things to work. So otherwise it will error out. So we can either use the reset all operation, or we can, if we know the state of qubit, then we can just apply the required unitary gate to make it 0. So this is about the clean qubits. Congratulations, you have completed an introduction to Q sharp now. And now you are ready to write powerful quantum algorithms, which Pallavi is going to show next. Pallavi, you may have it now.
Okay, sure. Okay, is my screen visible now?
Yeah, it is. Go ahead.
Yeah. Okay. So I hope that you people learned it and you are here, right, in the GitHub repo. So let's just launch it. It may take a while, so just wait for it to launch. We just tried to do it so that you people can start working without any setup, because it takes a while to do all the setup. So Binder is at ease. So thanks a lot, Rohit, for setting it up. So yeah, I'm still waiting for it to load. Okay. So here we are with the Jupyter. Let's create a operation. It has already explained it in a okay. Let's have a value. Now we are just
Excuse me, Pallavi, your voice is not clear, so can you please talk louder?
okay. Is it clear now?
Yes, it's clear.
Okay. Thank you so much for informing me. I will explain this using things, so I'm not gonna explain it. Also, we have this qubit setting default, as I explained by Tusha. Loop in this. This is really
So basically, Pallavi is writing here a quantum subroutine which is going to be run on a real quantum computer. So we are declaring an immutable variable by using the let keyword, which is number of rounds, and then we have two mutable variables, zero counter and one count. Then she allocates one qubit, and what is then we are basically iterating over 100 times. She is applying the Hadamard gate to create an equal superposition and then measuring the result. So nice.
also like we have default zeros and ones. We are going to use them as it is. We have explained about reset all and reset, so we really need to do it.
Oh, Pallavi, there is a mistake. You actually changed the variable name. It was declared as zero counter, and then you changed it to zero count. Okay, so no
Keep it.
problem.
Let's
So
keep it.
as I explained previously, quantum computers expect their qubits to be in zero computational state at the allocation. So let's say we measured it to be one inside the conditional statements, then it is going to remain one until the end of this block. But then after it's going to be delocated, then it is still in computational one state, which is wrong from a quantum perspective. So we need to reset them here. We can also use the X gate in the branch where result is 1. That is also going to work, but let's just say here.
So I missed semicolon somewhere. Let me see.
The problem is you on the second line you use let round, so make it rounds.
Okay, yes. Expecting a semicolon. Still missing a semicolon somewhere.
It's on the Hadamard qubit
Yes.
line.
Thanks, Rohit. Thanks a lot.
Yeah, you're welcome, Pallavi.
Okay, we are ready with this. It may take a while.
So basically, before running these quantum operations, they are needed to be compiled. So in the first cell, she wrote the quantum instructions and compiled it. Now we are going to call those somehow. So we have the second cell here, which uses simulate functionality to simulate that cell.
My network seems down. No, it cannot be down.
Pallavi, no problem. They are working. Just
Yes.
let them finish their completion.
So basically, each time you will be simulating, you will get different results. This is the specialty about qubits. I may need to reload it. So I think we should leave it.
Yes, we can get back to it when it finishes up all the computation.
Yeah, sure. We may proceed with Kahoot, I think.
All right, before we proceed to Kahoot, I would request all participants to fill a feedback form. I'll be sharing it in the YouTube chat. This is also a good way to get your email IDs so that we can mail you the certificates later on. Everyone will get participation certificates. So make sure you fill the feedback form, guys, before the Kahoot session. The entries will only be valid for the next 10 minutes.
Hello.
Yeah. Hello.
Hi, Anasuya.
Hi, Rohit.
Someone says the feedback forms link is not available. Well, guys, I can access it in incognito window as well. So it should be available. Oh, not able to click it. Okay. Do we have the simulation results here at Pallavi?
Basically the kernel died. I have to restart the kernel.
All right, all right. We can show them after the Kahoot session as well. Not an issue. All right, guys, we'll wait for 2 more minutes for the feedback form and then proceed for Kahoot session. Shall we get started?
Yes, I think we should get started, or else
All right.
there will
Let
people
me
will
share
just
my screen for Kahoot.
awesome. Daoud, yeah.
All right, guys, head over to Kahoot and join with this game pin.
Go to kahoot.it and when prompted to enter a pin, just enter 7426127.
So how do we identify the users at the end of Kahoot session?
I suggest, all the players who are right in, if you win the game, do not leave ASAP. Just, after you win the game, comment in the chat box with your username as well as your name and email address so that we can send in the special certificate that we have made for you.
All right, sounds good. I guess more people are joining. We'll wait for 1 or 2 more minutes.
Okay, by that time, I have the results with me of that computation which Pallavi was performing.
Yeah, you can go ahead and share the screen. Till then, people can join.
All right, all right. So, can you guys see my screen?
Yes, clear.
Yeah, it is visible.
Okay, so basically, we compiled this main operation. We are going through this loop 100 times and getting how many times 0 or 1 has occurred. So since quantum mechanics or quantum is the only way of creating randomness out of nothing on its own, so this is a classical example that yeah, this is true. So on first try we get 43 times 0 and 57 times 1. On the second try we have different results, and on the third try we have some other results. So this is sort of a proof of concept that here quantum performs in a can perform in a random way. Okay, so that's about it.
All right. Let's begin the Kahoot session then. Shall we get started, guys? Please comment in the chat box if you're ready. Okay, someone has asked in the chat what Kahoot is. Kahoot is nothing like it's nothing but like a quiz. Basically, you have certain number of questions and a time to complete a question, and the person who answers first the right answer will get a few points. And at the end of the entire session, at the end of the entire quiz, we will declare winners based on the number of points. Can we get started? Please comment in the chat box.
I think we have like a 16 people and 13 people are in, so I think we should get started.
All right, let's start then.
Farhan, can you also, just speak what the question is?
Okay, so let's let Farhan handle that. I'll just speak what the question is. Okay. So this question was, who proposed the quantum mechanical model? And the right answer was Paul Benioff. Many of you answered Richard Feynman. That's wrong, and the supposed answer is Paul Benioff. So moving on to the next question.
Yeah.
Okay. So after the first question, AEF is the first one, and then we have no one, and then we have Shaktiman. So all of these funny names, we won't be able to recognize you. So after the match, if you have won, paste in your details in the chat box so that we can recognize you.
All
and
right.
Send you special certs. Next.
Next question.
Which qubit lies at the heart of IBM? First is charge qubit, then Gnome qubit, then Transmon qubit, and then all. So the red one is charge, the blue one is Xmon, the yellow one is Transmon, and the green one is all. I'll just play it safe.
We have less answers right now. Yes, guys. Okay, moving along with the answers of our second question. The correct answer is 3. That's transform qubit. This is basically a special type of superconducting charge qubit that was designed to have reduced sensitivity to charge noise.
All right.
Yeah, now we'll move to the next question.
So in the lead we have no one, okay, and then AEFF and Preeti. All right. Let's go to the next question, guys. The next question is, although quantum computers are fast, traversing maze problem is still solved faster on classical computers. Is it true or false? Very simple question.
Yeah, and the answers came out pretty fast too.
Yeah.
So the answer for this question is false. That is the second
okay, wait.
option.
Anusuya, just a minute.
Yeah, okay.
Yeah, go ahead.
Okay, the traverse maze problems are solved faster in a classic computer. That's what this question meant. And let's move along to the next question, please.
Oh, we have Adil at the second place, AEFF, Preeti, and we have Zingsi as well coming up. All right. Next question. So next question is, quantum logic gates are question mark. Reversible, irreversible, none, and the next option is doesn't matter.
We have 9 answers so far. Guys, hurry up. Okay. The answer for this is answer number 1. Here the quantum logic gates are reversible because quantum machines is reversible, or let's call it unitary. That is why we have the answer as the reversible. And let's get into the next question, please.
Oh, we have AEFF and Zingsi coming up. Come on, Preeti and Adil. No one is still leading with 4,400 points. 426.
Yeah.
Next question. Which one among the following is known as gate of superposition? The options are Pauli X gate, Hadamard gate, C0 gate. Fourth option is none. Very easy question.
And the answers too came out pretty fast. Now we have 2 more. Guys, hurry up. So the jackpot answer is answer number 2, the Hadamard gate. This gate generally forms a uniformly random qubit that is given. It gives a random input, which basically means that a measurement will have equal probabilities to become 1 or 0, meaning it creates superposition.
All right. Thanks for the answer, Anusuya. The explanation.
You're welcome.
Oh, we have another player coming up, Sub. We have NAV and we have AEFF. No one is still leading. Who is this no one? Okay, next question. IBM and Microsoft have developed their low-level languages for programming quantum computers. They are options: Qiskit and Q Sharp, Quill and Quasm, Qiskit and PyQuil, Quasm and Q Sharp. It has a small trick, guys. Don't fall for it.
Okay, the right answer is Quasm and Q Sharp. That is answer number 4. Quasm formally defines a quantum circuit to render images for visualization purpose. With evolvement, it was used to specify quantum circuits as input into a quantum computer. QSARP is used for expressing quantum algorithms. This is a part of the quantum development kit that is provided by Microsoft.
Okay, I see that many of them have chosen Qiskit as the language. Well, Qiskit is not a language, it is an SDK, software development kit, just like we have QDK. So we didn't have QDK as an option for Microsoft, we had Q Sharp. All right. Ahead. No one is still leading. Then we have Sub and Zinxi, and we have Bot Crasher and AEFF following them. Next question. Which of the following is quantum equivalent of classical XOR gate, XOR gate? The options are Hadamard, C0, PolyY, and PolyX.
Okay, the correct answer is answer number 2. That is the C0 gate. This is a quantum logic gate which is used to entangle and detangle the EPR states.
All right. Madhav, would you like to add something to the explanation?
So the CNOT gate, as I had mentioned, has a target and a control. So the mathematical expression for the target is, if A is the control, B is the target, the mathematical expression for the target is A XOR B. So yeah, that's basically it. And C0 is also a universal gate, as you can model any of the gates using C0. So AND, XOR, or that can be modeled just using the C0 gate by varying target and control values.
All right. Thanks, Madhav and Anusuya. Let's move on.
Most welcome.
Oh, we still have no one leading. All right. And we have Bot Crasher coming up and Sub. Zinxi and AEFF follow. Next question. For n bits, the number of possible quantum states is, the options are 2 to the power n, 3n, n, and n to the power 2. This question is also pretty simple, guys.
Okay, the answer for this question is obviously the answer number 1, that's 2 to the power n. For your general knowledge, I want you to add up on this that as you add qubits, the power of your quantum computer also grows exponentially.
All right. Yeah, thank you. Madhav, I had a question for you. Uh, the answer here for quantum computers, when we have qubits, is 2 to the power n. Are there any scenarios where we can have 3 to the power n or 4 to the power n, where we don't have qubits but some other structures?
Yeah, so there's been some recent research and development in something known as a qubit. So you can have 3 to the power n there. So
All right.
instead of 0 and 1 distinct levels, you can have 3 distinct levels of voltages that you can operate at. So they're sort of using that in quantum communication and security, but they're yet to sort of get it to a moderately stable level to make use of it in actual applications. But yeah, a lot of institutes are doing work, especially I think theoretical work is being done by Raman Institute in India. So if any of you are interested, you can check that out. I think ICER Pune also, I'm not too sure about that.
Thanks, Madhav, for the insight into qubits. We still have no one leading, and followed by Zinxi and Bot Crasher. Sub and AEFF follow. Next question. Data is lost in quantum computer while gate operations are applied. Is it true or false? Very simple answer.
Okay, well, the answer many of you might already know, that's answer number 2. That is false. Data isn't lost in quantum computers while gate operations are applied.
All right.
Wow, we have a clear winner already.
Yeah. Next question. The final question, guys. How many qubits can you simulate using Microsoft QDK, a 16 GB memory? The options are 40, 30, 50, and 60.
The final answer is answer number 2, that is 30. The actual answer is 32, but when we round off, we consider it to be around 30. Rohit, would you like to further describe this answer, please?
Okay, Anusuya. So basically, we need to simulate, let's say, uh, 2 to the power n bits. So we are going to need uh, actually log of that number of bits. So in this case, it is 32, 2 to the power 32 amount of memory available. So 32 is the answer.
All right, let's see who the winners are. We have AEFF 6. All right. All right, so first place we have no one, second place Preeti, third place AEFF. Thanks a lot for joining us for the Kahoot session, guys. I would request the winners to add their name and email IDs to the YouTube chat, along with your username, Kahoot username, obviously. Madhav, do you have the answers ready from the coin flip challenge?
Yeah, just give me a second.
Yeah, sure.
Should I share screen?
Yeah, go ahead.
Okay. Can you see it?
Yeah.
Okay. So this is the result for the data that was collected, that was sent in by the participants of this session. So surprisingly, it's 50-50 chance of you winning or losing. So we got lucky there without the bias. But usually it's more towards one side or towards the other side. And coming to the quantum case, as mentioned, there's no chance that you can win. So there's always 100% chance that your opponent will win.
All right, 50-50. Yeah. Okay, guys, if you have any questions, feel free to add them to the YouTube chat. We'll answer it now. Do we have any questions? All right. Oh. Okay, Quantum Learner has asked, what are the next sessions going to be? Okay, so we have planned an entire QPower Quantum webinar series. So in the next series, we'll delve deeper into Q-sharp coding. We'll also delve deeper into quantum gates. So Today's session, Madhav explained, the surface of the math involved, the matrix operations and other things. But we will delve, like we will talk about in much more detail in our upcoming sessions. You can expect our next session to somewhere be in, say, next 2 to 3 weeks. And don't forget to like and subscribe to our YouTube channel, and also follow our LinkedIn and Twitter accounts, because we will be posting all updates over there. Thanks a lot to all the organizers. Thanks to the special guest Madhav for joining us and giving us great insights about quantum computing, about qubits, and about quantum gates. And all organizers, Ganesh, Pallavi, Rohit, Anusuya, we have Dibanjana, Vedant, Ricardo. Have I missed anyone?
Morsel.
Yeah, Mursal.
Web head.
Pardon?
Oh, I was talking about Mursal.
Yeah, Mursal, and all the other people in the QPower team who have helped us, and congratulations to all of them for organizing such a wonderful session. Thank you all, the audience, for joining us. You are a wonderful audience, and we are looking forward to your. We are looking forward that you can join us in the upcoming webinar series. Thanks a lot, guys. All right. Do we have anything else, or shall we end?
I think we're done with the session, and
All
the
right.
person no one is has replied on the chat,
Yeah.
and her
Oh no,
name is
Ganesh, I have the
okay,
credentials of
okay, okay,
no
okay,
one.
okay, okay. Awesome. So you can send the certificates over there. Awesome. So
So do we have
I
email
think I
addresses, all
will.
three winners?
Okay. Rohit, quickly, I wanted you to add the Discord server guild link so that they can join us over there. You know?
All right, Ganesh, on.
Awesome. Uh, any last words from anyone? Syed, do you want to say anything before I close the stream?
No, I think I'm done here. It was a great session by everyone.
Awesome.
Thanks a lot, guys. Okay, if we have no questions from the audience, then I think we shall end this session here. Thanks for joining. Bye bye.
Bye bye.
Thank you and bye
I
bye.
I will just go on to the VM and end this session. Wow. This is not supposed to be that hard. My internet is giving me problems right now. Awesome. So I'm into the live stream thing, and I got into the studio. Load, and yes, I have clicked on it.